Hey everyone, thanks for showing up here on a Sunday morning. I really do appreciate that. As you can see, the name of the talk here is Enough with Insanity, dictionary-based rainbow tables. My name is Matt Weir. I'm currently a graduate student at Florida State University. And pretty luckily there, my research is password cracking techniques. So that's actually what I'm writing my dissertation on, which is pretty fun, to tell you the truth. Before going back into academia, I actually did some work in real life too. I worked at Northrop Grumman Task as a network security engineer. But yeah, I won't go into that there. It is a good company, but a lot of times I do say we when I'm talking about my research, and that's because there's a lot of people I am working with right now who help carry me along quite a bit. So I want to thank them before I start. First of all, my major professor, Sudhir Agarwal, who gives me lots of really good ideas and then puts up with me, which is no minor task there, may I add. Edson Manners, who's another graduate student who's also doing some password cracking research. I'm going to briefly mention some of his research as well. The National Institute of Justice for funding this research. I really do appreciate that, so I don't teach Intro to C classes. Also, I'm going to get his name wrong, and I apologize. But Zhu Xuan Li, who wrote the original RCrack program. I want to thank him because all my stuff was pretty much based upon what he did previously. And finally, I don't think he's in the audience here, but RenderMan for providing the inspiration for this talk here and for this research. Because he came out with something with the Church of Wi-Fi called WPA Rainbow Tables. And they're not actually rainbow tables. They're really hash lookup tables, and I'll talk about the difference in a little bit. But I looked at that and I was like, that's really neat. Why can't we go ahead and do something like that with rainbow tables instead? Which kind of led to this whole project here. So as I said, my research is to actually do improve techniques in password cracking. And this is actually a very small part of my research here. A vast majority of it is we're trying to figure out how people actually create passwords in real life. So we spend a lot of time going out, collecting real password lists from disclosed attacks. So like a hacker will break into a site, they'll post all the password lists online, and we'll grab them and crack them ourselves and try to figure out how people are actually creating passwords in real life. So that way we can make better techniques to crack passwords with. Now, we're a little bit limited, though, in our actual password cracking lab here. We don't have that rack of PS3s or anything else like that. I mean, dude, I got a Dell. When I talk about this, please keep that in mind that when I say cracking something's hard, I mean that in the context of this here. So we don't have any distributed password cracking setup or anything else elite like that. So what we're designing, though, is for this type of environment. Now, I'm not trying to sell you anything, and since we are doing this as research, I want to go ahead and give all this information out for free. So, I mean, all the tools and tables plus my security blog can be found online at reusablesec.googlepages.com. I got the link on a lot of our pages as well, so you don't have to copy it down quite right now. Leave off the www, otherwise it won't work. Also, if you do have space to host additional tables, please talk to me afterwards, because I do want to post all of our stuff online as well. But I do got at least some of the basic tables online right now. Okay, so I do believe in putting a disclaimer in front of all my talks. And the main disclaimer for this talk here is I should not be giving it. I mean, it's 2009, and we're still talking about hash lookup tables. We've known for at least 20 years here how to prevent against this type of attack completely. And the prevention against that is just to use a strong password assault. And there's no trade-off really in doing this. There's no performance trade-off when using the password assault. There's no usability trade-off when using the password assault. Yet as a security community, we really can't seem to get this right, because here I am up here giving this talk, and it is still relevant because there's all sorts of people who are not doing this. It's easy to call out Microsoft because they have a spotty record in doing this in the past. You have the old Microsoft landman hashes, which were completely broken by brute force rainbow tables. Because they didn't insult them and a couple other problems. So they finally went ahead, they put a stake in the heart of landman, and now with Windows Vista, you're only seeing NTLM hashes. But even then, they don't use assault, so NTLM hashes are vulnerable against this type of attack. Well, for your MS cache hashes, these are your domain hashes, which are domain passwords there, which is really the keys to the kingdom. They did at least decide to go ahead and salt those. But they used the username because they figured that like no one would go ahead and construct a table against Bob in accounting. But unfortunately, there's this guy named Administrator. He seems to be really popular. He's on a lot of different networks. You know, people really trust him. So you can create tables against him. So that's kind of a fail right there. I mean, WPA2 for your wireless, they go ahead and salt it using the SSID. But once again, a lot of people name their network Linksys. So you get things like the WPA and WPA2 rainbow tables that RenderMan made that I talked about a little bit earlier. And then it's not just these big groups that are doing this either. As I said, we analyze a lot of disclosed password lists, especially from a lot of different websites. And most websites that we're seeing that get broken into, they're still using just straight, unsalted MD5, SHA-1, or MySQL 323 password hashes. So it's just across the board, people are not using password salts. And that's really just kind of disturbing to me, to tell you the truth. You got to make us work to crack your password, at the very least. And now something else, I might as well get some balls thrown at me here or something like that. But I really do believe that when it comes to password security, we need to stop blaming the users. I mean, I know, people choose bad passwords. People write them down. People don't care about security. Fire is hot, water is wet. We know this stuff. And I mean, all of the hoping and wishing and, that we've done here to want to get users to choose strong passwords just hasn't worked. Also, like all those security memos and meetings and stuff like that doesn't seem to be doing that much well either. So we need to go ahead and take this into account when we are going ahead and design our security strategies. And I'm not going to really talk about different authentication schemes and stuff like that because that's way beyond the scope of this talk here. But I mean, at the very least, we do need to be using strong password hashes. So if a site does get broken into, you raise the bar, you make it much harder for an attacker to figure out what these passwords are, and you protect the users. And by strong password hashes, number one, use a salt. I mean, I can't stress that enough. The other option there is to make the password hash much more computationally expensive. So instead of just going ahead and doing one iteration of MD5, you do 1,000, kind of like what's WPA. And if you've ever tried to crack like WPA and WPA2, you realize it takes a long time to make a lot of guesses. And that really does limit the attacker in what they can do as far as trying to break into the user there. Probably the best example that I can talk about for this, though, just came out this last Thursday, or at least it got disclosed. Anyone hear about the phpbb.com got hacked? Came out a little bit. About 40,000 users got their email addresses compromised. Or 400,000, I'm sorry, I misplaced the decimal point there. Well, one really interesting thing about this is that they were in the process of upgrading their database software. And the new database used a very strong password hash. It used password salt. It was slow to compute. But the old one had MD5 on it. So half the users were already, or actually more than them, half, were already put into this new database. And then the remaining were still left in the old database there because you couldn't change the user over until they logged in again. And so what happened was the attacker went ahead and he tried to crack all the weak MD5 password hashes. But he didn't even bother to try to crack the strong password hashes there because it's just too much effort. So yes, a determined attacker can attack these here, but it really does help secure you against a lot of the low-hanging attacks there. So I do have a tendency to kind of ramble on and get off topic. So just to give you an idea of what I'm going to talk about. I'm going to very briefly discuss password hash and salt. So hopefully if what I was talking about before didn't really make sense, it will after that. Then I'm going to talk about hash lookup tables and then rainbow tables in general and just to talk about the difference in how they work. And then finally I'm going to go ahead and talk about dictionary-based rainbow tables, which is the whole purpose of this talk here. So I don't mean to get all CISSP prep course on you here, but I just want to just go over this really quick. When we're talking about password cracking, there's really two types of password cracking, online and offline. Online, as the name implies, the system's still online, and you still have to deal with the security policies of the site. So a good example of this would be like the Twitter hack, where somebody found out the system admin's username, and they just went ahead and they tried a whole bunch of different passwords until they found out that the system admin's password was happiness. And then they went on like Paris Hilton's Twitter page and said, I'm a raging slut and stuff like that. But So I mean, that's an online attack, and the best way to go ahead and protect against that is just to go ahead and limit the number of login attempts per individual IP. And you can set this number really high, and it still will go ahead and limit the type of password cracking you can do on that. What we're going to focus on, though, is offline password cracking. So this is where you've already obtained the password hash. So either the police kick down the door, they seize the hard drive, or the attacker already gained root on the machine, or they did an SQL injection and just dumped the user database. So once you do that, you're really only limited by how much computer hardware you can throw at the problem. So with password hashes, how they work is that hopefully your website, your computer is not storing your password in plain text. If it is, then there's no need to crack the password. Once you break into it, you're done. So with a password hash, the user will go ahead and create a password, so in this case, Shmoocon, and the computer will go ahead and hash that password. So like the MD5 hash of that password is that big old long number there. And then hopefully it will go ahead and forget what the user typed in just as soon as it hashes it. Doesn't always happen that way, but it would be really nice if it does. And it only stores the MD5 hash, or in this case. So when the user wants to log in, they go ahead and type their password in again. The computer hashes that password guess, and then it compares it against the hash it has on file. And if those two hashes match, it lets the user log in. Now when you're trying to crack a password, you do the exact same thing. You just do it a whole lot faster. So you make a guess, you hash it, you compare it against the hash you're trying to crack, and if they match, you crack the password. In most cases, though, they don't, so you go ahead and make another guess, hash that guess, and try to crack it then. So as I've been mentioning salts, salts are a value that you add to a password in order to try to make it harder to crack. And basically, most salts, what you do is just a simple value you add on to the password before you hash it. And the reason for this is that if you don't use a salt, two users that have the same password are going to have the same password hash. So if both Bob and Tom go ahead and create a password and there's with the name Shmoocon, their password hashes are going to be exactly the same. So what a salt does, though, is in this example here, you could just concatenate their username onto their password before they enter it in. So this way, even though Bob and Tom both have the same password, their password salts are different. And this does a lot of things to go ahead and make your passwords more secure. As the first thing, as I said, is it does limit against hash lookup attacks. By the way, I want to stress, though, even though I'm using username in this example here, in real life you want to use a large random value. Don't use a username, as I said. Don't make Microsoft's mistake. Now, there's a lot of confusion about salts, though, so I just want to talk about a couple of them here. First of all, the password salt does not need to be secret at all. The secret part is the user's password itself. So the password salt is usually just go ahead and stored as a data field in the authentication database. Second, the user does not need to know the password salt. This is not something they need to type in. It's not something they need to have on their computer. As I said, normally it's stored on the server. So that way when it does a lookup and goes ahead and checks the username, checks the user password, it says, okay, this is salt, add that to password, and then compare it against the hash right here. Now the password salt should also be unique per user. And this is to really go ahead and help secure you against having someone audit a large number of users. So you break into a website, if the password salt is unique per user, it makes it much harder to go ahead and crack those passwords. And the reason for this is that if it's not salted, if you have, let's say, 10,000 users, you make one guess, you hash it, and you compare it against all 10,000 users. So if you have some really crazy password cracking setup, and it takes you, like, let's say, 1 day to crack a password, if it's not salted, it would take you 1 day to crack all 10,000 users' passwords. If you do salt it using an individual salt per user, though, you have to go ahead and make a guess, hash it for each individual user. So instead of taking just 1 day to crack all those passwords, it now takes you 10,000 days to crack all those user passwords. And I'll freely admit, when we're going ahead and auditing password hashes, by audit I mean crack, if we get a password list that's salted, we don't even bother with it, just because it takes so much time and I got one Dell computer to do this with. So it really does help secure you quite a bit. Okay, so CISSP stuff done. Now, hash lookup tables, most of the time you spend, when you're trying to crack a password, you actually spend generating the hashes. That's the computationally expensive part of password cracking. So bad guys realize, why don't we go ahead and instead of, hashing the same value to the same hash value every single time we want to make a guess, why don't we go ahead and just store all this stuff in a database? You know, so that way, if I get a password hash like CC25C whatever, I just go ahead and do a database lookup and say, okay, the password for that is monkey123. So that really speeds things up quite a bit. And password hash lookup tables are really, really nice. The downside of doing this approach, though, is that they're freaking huge. A good example here is, once again, you know, the Church of Wi-Fi's WPA rainbow tables. They're a really hash lookup table. They have a key size of 1 billion, which is actually 1 billion guesses is not a whole lot when it comes to password cracking. And the way you got the key size there is they have 1 million dictionary words, and they just hash it to get compared to 1,000 SSIDs because it's assaulted with SSID. And the file size for this is 33 gigabytes. So that does take up a chunk of disk space, though. Edson Manners, the other graduate student I talked about, though, is currently doing some research into this because disk space is getting a lot cheaper now. So, like, if you do have 8 terabytes of data that you can store, what's the best way to create hash lookup tables? And if you want to find out more about that, talk to me and I can give you his contact information. Because there's a lot of nice things about hash lookup tables that you can do. But, as I said, they are fairly large. So that's where we come into with rainbow tables, though. And really what rainbow tables are is just a very efficient compression function for hash lookup tables. So they reduce the size that these hash lookup tables take by several thousand. So instead of taking gigabytes, you're talking about megabytes of space in order to store this data, which is really nice. The major downside of rainbow tables, though, is they're lossy. And by that I mean they don't actually store, or they may not actually store all of the hashes that you're trying to crack. They generate them for. So that can cause a lot of different problems, which I'll talk about in a little bit here. Okay, so I'm going to go ahead and just kick it off a demo and then explain it a little bit more later because password cracking does take a lot of time and it's really boring. You can pretty much replace compiling with password cracking in this comic here, and it makes a lot of sense. It's great and wonderful to be doing research in this because, like, I'll launch a password cracking program, I'll go off for a week and feel like I'm being productive. So just to give you a real heads up here, the program I'm running, it's just a modified version of rcrack, so I added the D in front of it for dictionary-based rainbow tables. It actually does still handle regular rainbow tables as well. I give it the only difference really is I give it the -D option to tell it that it's going to be a dictionary-based rainbow table that I'm sending it. And then I'm giving it a config file instead of a rainbow table, mainly because I hated having all my information about the rainbow table stored in the name and having names like this long on my screen. So that's the one change there. And I'm just going to go ahead and try to crack a bunch of NTLM passwords. And I'll explain a little bit more of this later, but because this is a rule-based attack, there's multiple rules, so it shows you how many rules there are. So in this table is reading currently right now. There's 54 different rules. And it's a total key space of 26 billion that it's searching against. And it's trying to crack 8 password hashes right now. And we'll get back to that in about 6 or 7 minutes. Now, there's a couple things you need to know when you're talking about rainbow tables here. When you create a traditional rainbow table, there's 3 different values you need to specify. And getting the right, choosing the optimal things for these values is almost as much kind of like voodoo or magic as science right now, as far as I've been able to tell. But rainbow tables, they store all the password hashes in a chain. And we'll explain the chains in about 2 more slides here. But one thing you need to specify is the number of chains you're going to go ahead and have in your rainbow table. The more chains you have, the more hashes you're storing, but the larger the file size of your rainbow table is. The chain lengths, on the other hand, is just how many hashes you store in each chain. So it's essentially the compression function of your rainbow table. You make it too small, your rainbow table's huge. You make it too large, your rainbow table sucks as far as time goes. And then finally, the index offset. It's kind of overhyped a little bit, in my opinion, but it's a way to prevent collisions between multiple rainbow tables. And I'll talk about collisions in a second, too. So I want to have a quick note. There's one internal value in rainbow tables that's fairly important in the actual code. And it's called index value. And basically, this value just ranges between 0 and whatever your key space is that you're searching against. So each index value represents one password guess. So if you are, let's say, trying to brute force 6 characters in your rainbow table, all lowercase. Well, that's 26 different values. And since it's a 6-character long password, the number of possible values that range from is 26 to the power of 6, which is about 308, close to 309 million guesses. So in that case, your index value would range between 0 and then 308, whatever, minus 1. So each index value will represent one of those guesses that you could potentially make. Now, internally in the rainbow table, there's 3 main functions that make the whole thing work. Index to plain, plain to hash, and hash to index. And these are very cyclical type functions. The index to plain function, all this does is take an index value and tell you what plain text password guess is associated with that index value. So let's say you give it the index value of 2314, it'll return and say that the password associated with that is cat1. The plain to hash function is just a function, a fancy way of saying hash whatever guess you give it. So you pass it cat1 and it returns you the hash of whatever hash you're trying to crack in your rainbow table. And the final one is the hash to index function. And what this does is it takes a hash function and determines a new index value from that. So you pass it that hash value there and might say, okay, the next index value is going to be, let's say, 916. Now, when I said earlier, rainbow tables are based upon the idea of creating chains and storing passwords in chains. So the first thing you do when you're creating a rainbow, it does when it's creating a rainbow table, is it just chooses a random index. And this really is a random number that it just chooses that falls somewhere inside the index range. So in this case, it's 101. The next thing it does is it runs index to plain. So it goes ahead and just takes the index value and says what plain text password is associated with that. So in this case, it's cat1. And then after that, it goes ahead and runs plain to hash. So it hashes that password guess and returns that. And then from that, it goes ahead and runs hash to index to get the next index value it's going to go ahead and try. And so this is one step in the chain from the chain links that we talked about. And it'll actually repeat this the number of times you specified in your chain length value. So once again, after that, you run the index to plain again on that value, run plain to hash on that value, and then you run hash to index, index to plain, plain to hash, hash to index to plain, plain to hash, hash to index, and you just keep on continuing this until you reach your maximum there. So that's what it does when it's creating a chain in your rainbow table. Now, as I said, rainbow tables are a compression function. That's what you need to view them as. So, you're doing a lot of work here. Where's the compression? And the compression is that when you're creating these rainbow tables, you only need to store the first and the last index value. So you need to, once again, this iteration will be done thousands of times. And from those thousands of times and all this data that you create, you only go ahead and store those 2 values right there. So that's actually pretty good compression. Now you store the first value there because, because the way you create these rainbow table chains is deterministic. So if you have the first value, you can always recreate that chain. That's useful there. And then the last value is used to check to see if a password that you're trying to crack, a password hash you're trying to crack, will actually, or has the possibility of falling somewhere in that chain there, and whether you need to recreate it in order to try to figure out what the original password is. Okay, so when you look up a password hash, so you're trying to crack a password actually with one of these rainbow tables that you created previously. What you do is you take the password hash and you just run, hash to index on it. So now you have an index value associated with that password hash. And then you go back to your rainbow table and you check that second value of all of the different chains that you stored previously. And you try to see if any of those match. And if they do, you just go back and recreate that chain. And hopefully you'll see that password hash you're trying to crack in that chain. And when you do, you just go back one step and see what the plain text password was that created that password hash. Now, I'm doing a lot of simplification in here because there's a lot of different little things in this that, quite honestly, unless you're really hardcore and actually modifying the code yourself, you don't care about. But one thing that does affect people who are using rainbow tables is that the hash to index function actually changes depending on which step you are in the rainbow table creation process. And this is to prevent against collisions, because collisions are bad. But what this means is that when you're trying to crack a password, you have to go ahead and create a mini chain on that password based upon where that password hash might actually be falling in the a regular chain in your rainbow table. So when you first start trying to go ahead and crack these passwords, it first has to go ahead and create mini chains for each of the passwords to try to go ahead and see whether what the last value might be to go ahead and search your rainbow tables with. And this takes a long time. If you have chain lengths of 1,000, it would have to create 1,000 of these mini password chains for each password you're trying to crack before it even starts trying to crack the password. So when you first start trying to run rainbow tables, it seems like it just pauses for quite a long time, and that's what it's doing right there before it actually starts trying to crack the password. Also, because of this, when you're using rainbow tables, you really don't want to go ahead and submit 10,000 passwords to it at one time. I made that mistake once when I was first started using them, and I had it was like 20,000 password hashes I was trying to crack. So I submitted it to I came back a week later, and it still hadn't done anything, and I was like, what the hell? It must be broken. Of course, it's a problem with the program, not me. And also, I'll talk about this a little bit more later. But rainbow tables, when you're trying to crack a lot of passwords at the same time, they're really inefficient. They're really good when you're trying to crack a password, like only a couple passwords, and you have to do it over a long period of time there. So today I got to crack a couple passwords. Tomorrow I got to crack a couple more passwords. Next day I need to crack a couple more passwords. But if you have like 10,000 passwords you're trying to audit, it'd be faster to go ahead and just do traditional, whatever normal attacks you would, because that way you can go ahead and make a guess and compare it against all of the passwords at one time. Oh, I should have just gone to this next slide here. So rainbow tables do have a lot of problems associated with them. I'll free admit, unfortunately, you don't get something for nothing. The plus of rainbow tables is they're really small. The negatives are quite legion, actually. First of all, they are probabilistic in nature, as I said before. So even though you might have that big old index space that you're searching against, based upon the essentially the random nature that generates these chains, you can't be guaranteed that the password hash you're going to try to crack is actually going to be inside that rainbow table there. And because of that, one strategy that we use in order to try to combat this is make many, many, many more guesses than we normally would need for the key space there. So that way, it just raises the probability that the password hash eventually that I want to crack is actually going to be in the rainbow table that I created. But what this means is that rainbow tables take much longer to go ahead and create than a hash lookup table. So you're talking about an order of magnitude more time to create a rainbow table than to actually just do a search against that normal key space there if you're doing normal password cracking. So you only want to create rainbow tables against password hashes that you're going to be searching for a lot. Also, as I mentioned earlier, 2 password hashes when you're trying to crack them with rainbow tables take twice as long to crack as 1. So once again, if you're trying to crack 10,000 password hashes, rainbow tables are not for you. Okay? And also, collisions result in a lot of wasted work. So I'll mention that in this next one here. As I've been saying, collisions are bad. And basically what I mean a collision is that while the password hash that you're trying to crack may be resistant to accidental collisions just because of it's so long, your index value is not. Because your index value, you're hopefully going to be making guesses over every single possible value. So the hash to index function that you use often results in 2 different hashes, or many more different hashes, creating the same index value. And this is what is called a collision. If these this collision occurs in the same point in 2 different chains, or more the chains, it says these chains merge. And basically what that means is that every single guess after that collision there, the chains are doing the exact same work, so you're just wasting time. Furthermore, this results also when you're trying to crack a password in false alerts, false positives, because a collision will occur and then it'll look like the password hash you're trying to crack is in a chain, but it really isn't. So you'll spend a lot of time recreating that chain only to realize that your password hash you're trying to crack isn't there. So when you're creating these rainbow tables, you really want to minimize collisions as much as possible. And that becomes even more important when you're doing dictionary-based rainbow tables, which I'll mention when I get to that there. So your traditional rainbow tables that you see most of all, their index to plain function just does results in brute force guesses. So you can say, you know, I want to brute force all, you know, 6-character words of upper, lowercase, special characters, and numbers, and it'll do that. So it'll create guesses like, you know, AAA, AAB, AAC, and so on. Now, this is still really nice. I mean, landman passwords are completely broken by this approach here. And, I mean, brute force is a very nice attack to be using. But there's other password hashes out there besides landman. So the next improvement that someone created over at freerainbowtables.com was it's called rcrackI, but they use hybrid rainbow tables. And basically, this is a targeted brute force attack. So instead of being stupid about your brute force, you try to use some information about the users, because users tend to create passwords the same way. So what it allows you to do is say, create tables based upon, I want to go ahead and create, you know, 4 letters followed by 2 numbers, because people always put numbers at the end of the password. Or for uppercase, you know, people always uppercase the first letter, but they don't uppercase like all the other letters. So why should I spend time with brute forcing, you know, trying, you know, all these combinations that people just aren't going to go ahead and create? So this allows you to go ahead and essentially try kind of a miniature brute force on much longer passwords, and this is extremely effective for cracking passwords that are, you know, 8, 9, even 10 characters long sometimes. So for my dictionary-based rainbow tables here, really all I did was just modify the index to plain function there to set, you know, instead of choosing a random, you know, letter, to just grab a dictionary word and apply whatever mangling rule it is to it. And I'll freely admit, not rocket science at all. And I made a few other improvements as well, because a couple things just annoyed me about it. But I mean, that's really essentially all I'm doing. So all the previous slides there, it's just the same thing. Instead of doing brute force, I'm grabbing a dictionary word and applying a word mangling rule to it. So let's go back to the demos here and see if it actually blew up or not. Oh, cool, it actually did. Sweet. Okay. So the first thing I want to point out here is of these 8 password hashes, it only cracked 6 or 5 of them. So, I mean, the first thing is, oh, God, you know, this guy can't even get a pre-canned demo to work right. I mean, he really does have to suck, you know. But one thing I want to stress is that these rainbow tables here really only, they face the same limitations as, you know, your traditional, you know, dictionary-based, you know, password cracking attacks. If a user went ahead and created their password based upon a non-dictionary type of approach, this is not going to work against it. If they created a password and it's not the dictionary word's not in your dictionary that you're using, you're not going to crack it. If they did a word mangling rule and you don't go ahead and apply that right word mangling rule to when you're trying to create these tables, it's not going to crack it. So this is not. I don't want to see anybody, you know, writing a blog post or something like that that says, you know, passwords are completely broken by this attack or something like that, because they're not. So you do have to go ahead and when you create these tables, try to take that information into account. One other thing I want to point out here, so like the passwords that cracked here, it was like test, password 1 was capital P, you know, password 1 was the A replaced with an @ symbol, password was 2 stars at the, you know, on each side of it there, and then, you know, infrastructure/technology 13 with, you know, capital I. And I'm actually going to get back to it when I'm talking about passphrase cracking here, but this is not anything like LEET. Like, I don't have a rule like take 2 words and add a slash into the middle, you know, and capitalize the first letter and then add 2 numbers to the end. But infrastructure/technology was actually in my input dictionary there. So not nearly as cool as that. But the nice thing about this, though, is you can go ahead and feed it multiple rainbow tables. You can create rainbow tables based upon different types of passwords and dictionary attacks that you're trying to do. So even though I didn't crack those first 3 ones with this approach right here, I can go ahead and, I can just change the rainbow tables it's going against and try to get some other rainbow tables that I created. So like, I created one off of keyboard combinations. So you can go ahead and try to crack passwords that way too. So I did say I did make a few other improvements to this because there's a couple things that annoyed me. And also, as I said, I only got 1 computer. So I tried to make this a little bit more efficient because I'll freely admit I'm not the best coder in the world. So when I modified the index to plain function, it's much slower than the traditional brute force approach. So I wanted to go ahead and speed it up a little bit more to kind of negate that problem. So the first thing is I multi-threaded the rainbow table creator because that's an extremely parallelizable process. So that way you can take advantage of all those multi-core CPUs you have when you're creating these rainbow tables. I also added faster hashing algorithms because the original RCrack used OpenSSL. So I went ahead and grabbed some more optimal password hashing algorithms to use for that. At the same time, I added support for additional hash types as well, so you can crack other types of password hashes. As I mentioned before, it also uses config files, so that way you don't have file names that are huge. So, and that way you can also look into the config file and tell what different things are. And I also added a version info into that as well, so that way we can make improvements to this, but actually have our old tables still work, which is also fairly important there. And then I did a bunch of other tweaks and optimizations that I'm not going to bore you with. Now, I don't claim to be the only person who's done this. I started working on this, and in fact, I actually wanted to get this into last year's Shmoocon talk, but I didn't have it anywhere near close to done. But other people have come out with a dictionary-based rainbow tables too, so if you look at my code and say, this sucks, which is definitely a possibility, you can go to these other people as well. That's not RCrack. Yes, RCrackD is a guy came out with that and is posted on freerainbowtables.com. And then OffCrack, they're free Vista rainbow tables, which is NTLM. They actually are using a dictionary-based approach as well. Unfortunately, it's OffCrack. You actually have to pay if you want additional tables from them, which kind of sucks. Now, a couple things about creating a rainbow table. I'm not going to do that in front of you right now because that'd be probably the most boring presentation ever. It's like, look, it's still working. But there's a couple things I found just with doing traditional password cracking that I tried to optimize here to make it easier for people to use. And the first thing is I've made a GUI-based rules generator instead of just a command, a scripting type rules generator. Because I mean, I love John the Ripper. It's my favorite password cracker ever. But it annoys the hell out of me because every single time I mention it, people are like, "Oh God, the config file for that sucks. I can't figure that out. I may know like 8 scripting languages, but I can't read a simple rules file." So one tool I have actually on my website, just because I got tired of all the bitching, is I made a GUI-based John the Ripper config file generator. So that way you can say, I want to go ahead and create passwords and add 2 numbers to the end and capitalize the first letter. And I made some other improvements as well, such as you can first of all save and load the configs, so that way you don't type them in each time. But you can modify the configs for different password rule creation strategies. So if the group that you're trying to break into has a password creation policy, you can take your normal rules file and say, I only want to try password guesses that are at least 8 characters long, contain uppercase, lowercase, and a special character. So that way you're not making guesses and wasting your time on passwords that it's not going to be. Also, I add support so you can quickly change between different language supports as well. So because it seems like all password cracking programs out there are made against English, and I kind of want to spread the love a little bit there. But I'm a lazy person. I really don't like reinventing the wheel. So I pretty much just took that config file generator there and it's made it, converted it to the rainbow table one. And I add a few different new rule types that John the Ripper doesn't really support very well to it. Now, one thing I really just kind of want to note is that when you're creating these rules here, it is extremely important that you try to reduce collisions. You try to reduce duplicate guesses. Because, as I said before, collisions are bad. And it's really easy when you're creating your rules to go ahead and generate rules that create lots and lots of collisions. For example, you might have 2 rules in your, that you're trying to do. Try the word as is, which is a very common rule, and then lowercase all the word, lowercase the entire the guess, and then try that. So, I mean, that creates lots of collisions, because if you have the word password in your input dictionary, it's going to try password twice, once for each rule there. So you really want to go ahead and avoid that type of stuff. Also, it's extremely important for your input dictionary that you send it, that you go ahead and you remove duplicate words from that, because once again, that generates a lot of collisions. So it does require a little bit of work up front to go ahead and a little bit of thought when you're going ahead and generating your rainbow tables here. So, I mean, I'm releasing all my tables. Hopefully I'll get more and more of them online as I get more disk space. But a couple of the tables we've already created, we have our basic NTLM and MS cache passwords. So once again, this is for your Windows logins, both local and domain. We use DIC0294 for the input dictionary because that's one of the the best online, readily available input dictionaries I've found so far. And it has a key space of about, oh, okay, watch out. Key space of about 26 billion. But the actual space of all the rainbow tables, and I actually made a whole lot more just because this is more, collisions occur more often in dictionary-based rainbow tables than traditional rainbow tables. And even then, all the rainbow tables that follow this are only 400 megs. So just going back to the WPA rainbow tables, or hash lookup tables, that had a key size of 1 billion and a disk space size of 33 gigs. And now you're talking about a key size of 26 billion and 400 megs. So that's why you use rainbow tables. But as I said, hash lookup tables are really nice, especially when you're talking about large, strong password hashes. And just a couple sample rules. It doesn't do anything, extreme, but it does stuff like add 4 digits to the end, or standard letter replacements, and then add special character and a digit to the end, or like capitalize the first letter, standard letter replacement, and then add special character and digit to the end, and so on. And it said it's got 56 different rules in that for it. Another one I made was a keyboard combo table. Because what I'm really interested in is cracking strong passwords. Because it seems like everyone's moving to the 15-character passwords and stuff like that. So that's what we need to be targeting right now. And once again, we're not targeting the encryption algorithm or anything else along those lines. We're attacking the user. Because there's a lot of users out there that are going to choose poor passwords. Now, going back, it seems like whenever I talk about password cracking, I always have people come up to me and say, hey, Matt, my password here is, I do this, and then I do this, and then this is what I do for my password and stuff like that. Can you crack it? And my first response is, well, thanks for telling me your password. Where do you do all your online banking? Because I'm poor. But my second response is, yeah, I'm not probably going to be able to crack that password there because you're doing some really crazy stuff, and I'm just not going to have a rule for that. With password cracking, though, for the most part, you are trying to attack, the chief information officer or maybe somebody else, a guy in charge of business or whatever, who's choosing the poor passwords. Because there's a lot of people out there who are still using password 1. If you give them a strong password creation policy, they're going to go ahead and use similar shortcuts. And that's what you want to attack. Now, one thing we've seen a lot of is keyboard combos. And people basically just add more keyboard combos to that the longer the password they have to create is. So this table here, I actually made 2 separate ones. One that's fairly small and pretty easy, quick to check. First of all, I made a custom dictionary. It has 658 different types of keyboard combos, like QWERTY or 1, 2, 3, 4, and so on. And the first table just goes ahead and tries 1 to 3 of these combined. So it'll try like QWERTY and then like 1, 2, 3, and then maybe shift Z, X, C, V, or whatever. And so it combines all those. And then I have another one that tries 4 keyboard combos. Just so you know, when you start combining those, 658 to the 4th power, it actually starts getting to a fairly large key space there. The downside of this is that, and I didn't think about this until I started creating this, is it does have a lot of collisions. Because unfortunately, when you start adding different keyboard combos together, there's a lot of overlap between the different types of keyboard combos you have. But still, it's actually fairly efficient for looking up those passwords there. Another way I would like to go ahead, I've seen people when they have to create 16-character long passwords, is that they'll take an 8-character long password because they can remember that, they've been using it everywhere, and just double it. So they'll type it in twice when they're logging into a site there. So, I mean, that's another rule we can definitely go ahead and mimic. So I have this double basic rule, is kind of like double secret detention and stuff like that. But all it does is just do the standard basic rule, standard dictionary, stuff like that, and then just repeat it twice. In order to go ahead and try to attack that. So once again, we're just attacking the user here. Passphrases, this is actually what I'm currently working on right now because there's not a whole lot out there to attack passphrases. But the most basic way to attack passphrases there is that, once again, if someone uses a passphrase, the majority of users are still using like the words password1 and stuff like that. They're not going to go ahead and create a custom one. They're going to go ahead and use ones that we can see and find out already online. And we've actually seen that in a couple of the cases we've done. So you'll have someone who'll take a passphrase like it's fun to do to impossible or something like that, and they'll just do a very simple word mangling rules around it, like add 2 bangs to the front and 1 bang to the end. This is actually from a semi-real case and just modified it a little bit. But I mean, that's the type of password people are actually creating there. So I mean, we can definitely target this. You just need to go ahead and have the basic passphrases in your input dictionary and apply whatever word bangling rules you want to them. Now, doing passphrase creations, I guess by almost like a brute force attack where you just grab, like I want to try 8 different words, gets ridiculous really quick. Just because if you have a large input dictionary and you try to do that just stupidly, the number of guesses just grows exponentially, literally. So what I'm also trying to add right now is support for grammar generation, because people make passwords in certain different ways. So you can have multiple input dictionaries for when you're creating your rainbow table here. And just take one, like, and then instead of rules, you have, grammars. So instead of trying, like, all, just 4 combinations of different words here, you can do, like, proper noun, verbs, and noun. Fill in verbs, or whatever verb you want there. So this is kind of like Mad Lib. And this reduces the size of your key space quite a bit while still attacking people. And you can get even more specific to that, too. Like, for example, we see a lot of passwords like Mindy loves James, or, Bob loves Sarah. Hopefully he's actually dating Sarah at the time. But so you can definitely create strategies to go ahead and attack users like that there. Now, I don't claim that these are like better than existing rainbow tables any more than I claim like dictionary attacks are better than brute force. I mean, they all have their places. So it does not replace additional tables, but you can use it in addition to the tables that are currently already out there. In fact, I add a few features to this, like don't try password guesses less than 8 characters long. So that way you can generate your rainbow table against 8-character long passwords, and then you only spend your time with these dictionary-based tables attacking passwords longer than that. So any questions or comments at all? Yep.
Have you played around with programs like Wiz that generate custom password files?
Yeah, that's on the backtrack CD there, the with.pl there. It's actually it's fairly nice. It doesn't have a lot of logic built into it, but that's actually fairly hard to do. We made some custom tools to like scrape Wikipedia to create like so you want to create, find someone who's interested in like beer, video games, and porn or something like that. It'll go to the Wikipedia articles and grab that information down. Actually, we found though it requires a lot of work, because if you go to like the Wikipedia article on beer, you'll get a whole lot of information on like the fermentation and history of beer. But you actually need to find a different article on like the different beer brand names. Yep. But yeah, the wid's pretty nice because it strips out all the HTTP headers and stuff like that from when you download off of web pages there, because those just result in junk guesses there. So yeah, that's a good question though.
How prevalent is password cracking these days, given that one of the most common attacks you see is pass the hash?
Not very much at all, actually. It helps the good guys more than the bad guys, which makes it easier when I have to explain this to our human ethics committee at our college there. But yeah, the bad guys, I mean, they have pass the hash, which, I mean, when I first found out about it, I was like, that's cheating, okay? I mean, you don't even need to crack the password. You just grab the password and submit it, or password hash and submit it. But hackers don't play fair, apparently. So yeah, like in a Windows environment, the hacker doesn't need to crack the password. And then you have all different other things where like keystroke loggers. That's really not available to law enforcement, and I'm kind of happy with that. But I mean, bad guys are definitely going to be using that as well. So I mean, password cracking, we're seeing that more for law enforcement, especially a lot of them, like if they have encrypted files on the hard drive. So we're not talking about like a full hard disk encryption, but just regular encrypted files. People use the same password. So the very first thing they do is try to attack the Windows password and find out what that is, and then try that against the encrypted file there. So, but yeah, as an attack, we're not seeing that a whole lot. Except you see a lot of people when they break into a site, they'll try to crack the passwords and post them online, just, so how cool we are and all this other stuff. But as far as the serious attacks, no. Any other questions? Cool. Well, thanks for showing up here early on a Sunday morning. Oh, cool. Yeah, you cracked the other passwords here of keyboard combos there. Yeah. I mean, yeah, for an attacker, it's a waste of time,